Okay, in this video, I'm going to go through AQA AS-level Chemistry, the 2019 paper, and this is paper 2, and this is the second half of the paper. The first half of this paper I did in an earlier video. Okay, so starting off here with question 8. Okay, this is a type calculation. Right, propanol can be prepared by the oxidation of propanol with acidified potassium dichromate, which you've got there. And they give the equation there for the reaction. There's the acid you need to make it work. Dichromate is, of course, reduced to that green chromium ion there. Okay. Calculate the minimum volume in centimeters cubed of 0.4 mole per decimeter cubed potassium dichromate needed to oxidize 6 centimeters of propanol to propanol. Right. So first of all, we need to work out the moles of propanol we've got. And first of all, we need to work out the mass. So we've got to use density, of course. Density is equal to mass over volume. So our mass is equal to density times volume. The density, they tell us, is 0.8 grams per centimeter cubed. And the volume is 6 centimeters cubed. So all our units are okay there. Don't need to convert them. So that is going to give us a mass of 4.8 grams. Okay, now let's work out our moles of propanol from that mass. So moles propanol is equal to the mass divided by the MR. The mass is 4.8 grams and the MR is of propanol is 60, they tell us. Okay. Okay, so that gives us a value of 0.08 moles. Okay, now let's look at the equation. We need to say how many moles of dichromate solution do we need for that. Right, so 3 moles of propanol only need 1 mole of dichromate. So our moles of dichromate then we need is that divided by 3. Moles of the dichromate. 0.08 over 3, which is equal to 0.0267 moles of dichromate. So we know the moles of dichromate. Now we know the concentration of the dichromate, so we should be able to work out the volume. So let's do that. So concentration, let's do green. Conc is equal to moles over vol. So the volume in dm cubed is equal to, volume is moles over the concentration. So that's going to be 0.0267 divided by the concentration, which they tell us up here is 0.04. That works out to be 0.0667 dm cubed. So multiplied by that 1,000 to give us centimeters cubed, 66.7 centimeters cubed. Okay, it doesn't say anything about significant figures. 3 sig figs will be correct though. 66.7. Right. Now, this reaction is done in a pear-shaped flask. And here, you've got to complete the diagram. We want to oxidize the propanol just part way to propanol. We don't want to go, of course, if you get a primary alcohol, if you've got propanol, you oxidize it first to propanol, and the second step of oxidation to propanoic acid. We want to stop it at the propanol there. So what we've got to do is we've got to get the propanol away from the oxidizing agent. So we need to distill it off. Okay. If you wanted the propanoic acid, of course, I'm not asking you this, but you would have to reflux for that. So it says complete the diagram, and they give you a pear-shaped flask, and you've got to label the diagram. So what you've got is you have a pear-shaped flask here. and you'd have that connected to a ground glass connector like that. You'd have a thermometer in there, and then you'd have a ground glass connection here to a condenser. There's our condenser. Okay, now we have got our dichromate and our propanol in there. We're going to heat that up, and the acid, of course. We're going to collect our product here, so we have a little connector there. And here is going to be our product. This is the propanol collecting here. We really should label this condenser, label it a condenser. I won't write that on it. You also need to put in the water goes in at the bottom there. The cooling water goes in there and it comes out at the top. So you need to label condenser, thermometer, connector, pear-shaped flask, this connector, and then the final product. And if you look in the mark scheme, you've got to make sure that all these joins are all kind of drawn as being airtight, because if they're not, the experiment wouldn't work, and they'll knock marks off for that. The main thing is to realize it's distillation and not reflux, though. Yeah. Okay. Right. So we've got a fluorocarbon CFC, chlorofluorocarbon there. And they can break down the upper atmosphere to form chlorine radicals. Okay, and of course they can go on to cause depletion of the ozone. They're probably going to ask about that next. But first of all, give an equation to show the breakdown of one molecule of 1,2-dichlorotetrafluoroethane to form one chlorine radical in another species. Okay, so here let's draw. So I would draw it. Let's have it. We can write down CClF2, CF2Cl, and then write it like that. You can draw it displayed if you like. They'll allow that. And we're going to give some UV light, and we're going to basically break off. We're going to break that bond there. So that bond there, the pair of electrons there, one is going to go to the chlorine to form a free radical, and it's going to leave another free radical behind. And the free radical leave behind is going to be CClF2, CF2, and I'd put a dot on my carbon there. They probably let you put it elsewhere. That's to show it's a free radical. And you've got a chlorine with a dot. That's also a free radical. Right, now give two equations to show how chlorine radicals catalyze the decomposition of the ozone layer. That is basically a recall question. So you just need to know what happens. You get a chlorine free radical that reacts with an O3, an ozone molecule, to give this free radical, chlorine oxide radical, and you can have an O2 molecule. Okay, then the free radical formed in that first step reacts with another ozone molecule to reform the chlorine free radical, and you get two O2 molecules. Okay, so you can see it doesn't ask you that one chlorine is acting like a catalyst, if you like, and it doesn't get used up, it gets regenerated, so it can cause many molecules of ozone to decompose. Okay. Right, butane can be used as a replacement for CFCs and refrigerators, and during its use, the butane repeatedly turns into a liquid and then to a gas. Okay, and when it turns into when liquid butane expands, it will turn into a gas. We've got to calculate the difference in volume. So first of all, we've got to calculate the volume of that much butane gas using the ideal gas equation. Then we've got to work out what volume it would occupy as a liquid using density, and then we've got to compare those two with a factor. It's a big 6-mark question. So let's first of all do the red bit. Let's work out the volume of the gas. We're going to have to use the PV is equal to nRT. We want to work out the volume, so rearrange to give us V is equal to nRT over P. Right, now N is the moles of butane. Right, and moles of butane is going to be equal to the mass of butane over the MR. Okay, now we've got 38.8 grams of butane. And butane, right, they don't give you the formula butane, but so you've got to know that it is C4H10. I'm sure you know that. And so the MR of that is going to be 58. So it's going to be that divided by 58, which gives us 0.669 moles. Right, now before we put anything into our ideal gas equation, we've got to remember the units. This is where all the mistakes are made in the ideal gas equation. Right, so this volume is going to be in meters cubed, so we're going to have to convert it. We want centimeters cubed at the end. Okay, that's in meters cubed. The temperature is in Kelvin, so we're okay because we've already got that in Kelvin. But this pressure, we have to be careful. That's 101 kilopascals. That needs to be in pascals, not kilopascals. Okay, so let's put the numbers in. So we get V, our volume, is equal to 0.667 multiplied by 8.31 multiplied by the temperature, which is 272, divided by the pressure, which is 101,000. That gives us an answer of 0.01497 meters cubed. Okay. Right. Let's convert that into centimeters cubed. And people always forget, don't forget that 1 meter cubed is equal to a million centimeters cubed. So how do we convert that? Times it by a million, times 10 to the 6. That gives us 149,071 centimeters cubed. Now, I normally would not leave that to that silly number of sig figs, which is 5 sig figs. We're going to use it later on, so maybe you should round it. Maybe you're not going to knock marks off anyway, but I will round it up. That's going to be 3 significant figures, 150,000 centimeters cubed. That's the volume of the gas. Right, now the next thing we need to do is we need to work out the volume of the liquid. Okay, so how are we going to do that? Well, we need to use density is equal to mass over vol. And we have to be careful with the units here. Right, so the volume in centimeters cubed is going to be equal to the mass divided by the density, because the mass is measured in grams and the density is measured in grams per centimeter cubed. So there we're going to have the volume is 38.8. That's the mass of butane divided by the density of butane, which is tell us is 0.6. So that's going to occupy a volume of 64.7 centimeters cubed. Now, for the last bit, we need to say, look here, we calculate the factor by which the butane expands in volume when it changes from a liquid to a gas. Okay, so factor is going to be equal to the volume of the gas, which is really big, in centimeters cubed, divided by the volume of the liquid, also in centimeters cubed in the same unit. So that's going to be 150,000 divided by 64.7, which is going to give us a pretty big number. That gives us 232 is the factor. So its volume increases by a factor of 232. That's quite an unusual question, that one. Different to other ones. Okay, now we're on to the multiple choice section of this paper. Okay, so, right, drink driving offence is 80 milligrams of ethanol per 100 centimeters cubed of blood. And we've got to convert the concentration into moles per decimeter cubed. Okay, so the first thing we're going to do is I'm going to say right, the moles of ethanol. Sorry, so the moles of the moles of ethanol in 100 centimeters cubed. That's going to be mass over mR. Right, the mass is 80 milligrams, so that's equal to 0.08 grams. The mR of ethanol is C2H5OH, so the mR is 46. That gives us 1.739 times 10 to the minus 3 moles. That's in 100 centimeters cubed. So let's work out the concentration in moles per decimeter cubed is equal to the moles over the volume in dm cubed. So 1.739 times 10 to the minus 3. 100 centimeters cubed is 0.1 dm cubed. So that's going to give us 0.01739. Okay, so that is going to give us C as the answer. That's the closest one there. Okay. Okay, this is about the Boltzmann distribution. I'm just going to sketch that. Okay, so the Boltzmann distribution will be something like that. Okay, so that's the energy, the number of particles, or the number of molecules. Okay, so molecular energies. Right, the curve is symmetrical. No, it's not about the maximum. Look, it's skewed to the right. There's the maximum there. There are always some molecules with zero energy, right? I haven't drawn it really well there, but no, that's wrong. That line goes through the origin. There are no molecules with zero energy. That's wrong. That's always got to go through the origin, that line. The position of the maximum of the curve is not dependent on the temperature. Well, it is, because if you increase the temperature, the average energy that is going to move across like that, isn't it? It's going to be lower as well, yeah? So that's wrong. The mean energy of the molecules is greater than the, let's see that. The mean energy of the molecules is greater than the most probable energy. Now that is true because this is asymmetric. That's the most probable, but you can see there's more, it's kind of heavy to the right, this curve, isn't it? So the mean is going to be somewhere probably about, there's the most probable energy, and the mean is going to be slightly to the right of that, somewhere like that. Okay, so that is the answer. And it's all down to the fact that that curve is asymmetric. It's skewed to the right. Right. Okay, this is an equilibrium one. That's why I put this little grid down. So 1 mole of ammonia is heated, 50% of it dissociates. So let's start moles of ammonia. We're going to have it says we've got 1 mole, isn't it? So we've got 1 mole of ammonia to start off with. So let's put down there, start moles, we've got 1 of that, we've got 0 of that, we've got 0 of that. When equilibrium is established, 50% of it dissociates. So how much have we used up? We've used up 0.5 of a mole. So how much we've got left over? We've got 0.5, right? So how many moles? 1.5 mole of ammonia is going to give us 0.25 moles of nitrogen. And it's going to give us 3 times that amount, 0.75. So that should go there, 0.25. And it's going to give us 0.75 of hydrogen, 3 times that amount. So add these up together, 0.5 plus 0.25 plus 0.75 gives us 1.5 moles. That's the total moles of gas. So A is the answer to that one. Okay, which compound is not an isomer of the following compound? Okay, so we have got 5 carbons there. 1, 2, 3. So we've got 4 carbons there even, yeah? We've got 4 carbons. So is there any not with 4 carbons? They've all got 4 carbons, so that's not that much help. Now, let's think about the number of hydrogens there. Well, we have got 2 hydrogens there, 2, 4, 6, 8. So this is going to be C4H8O. Right. Now look at the ratio of carbons to hydrogens there. Can you, because it's cyclic, it's CnH2n. It's not 2n plus 2. It's not that. Okay. That's because it's cyclic. Now what else causes it to be CnH2n is, if other than cyclic, is when you've got a double bond, one double bond. And that can either be a carbonyl double bond or a carbon-carbon double bond. So we're looking, all of these isomers have got to have just one double bond in them. So which one is not? Okay, this has got a double, it's got a carbonyl in it. That's okay. This one has got one double bond there. It's got carbon-carbon. This one's got an aldehyde, so it's got, yeah, it's got one there. This one has got two double bonds though. This has got a double bond there, and it's got a double bond in the aldehyde. So that would actually not be C4H8, it'd be C4H6, that one. So that one is not an isomer, so that's D. Okay, it's very useful, this CnH2n thing. When you've only got carbons, hydrogens, and oxygens, it tells you how many double bonds you've got in it, or either double bonds or cyclic structures. It's useful. 14. Okay, how many isomers are there of C3H9n? I don't think this should be in the AS paper because it not only involves primary amines, but it involves secondary and tertiary amines, which are not really till year 13. But let's see what we've got here then. Right, what could we have? We could have, right, we're going to have 3 carbons in a line. That makes it easier because we can't have any branches. There's only 3 with 1 NH2. That's called a primary amine group there. So we've got 1, 2 hydrogens, 3, 4, 5, 6, 7, 8, 9. So we've got 1 there. We could shift that NH2 group onto the middle carbon there. That would be another isomer. Now, they're both primary amines. The other thing we could do is have the nitrogen bonded to more than 1 carbon atom. So I'm going to put my nitrogen there. Nitrogen, of course, always forms 3 bonds. So let's have it, let's say it's attached to 3 carbons. Okay, so you could have CH3 there, CH3, and CH3. That would be an isomer. Okay, that's another one. And that's the only thing you can have with the nitrogen attached to 3 carbons. I'm sure you can see that. But we could have some structures with the nitrogen only attached to 2 carbons. They're called secondary amines. Okay, so I could put, right, we've got to have 2 carbons. There's, right, 2, well, there's 3 altogether. So the only thing I can do is put 1 there. Okay, and that would be the structure. And of course, that's the only thing I can have with a nitrogen bonded to 2 carbons. You know, it's got an ethyl group on one and a methyl on the other. So that's 4. So the answer there is 4 isomers. Okay. 15, about substitution, which represents a propagation step. Now, in a propagation step, you always get something which is a free radical that reacts with something else that isn't a free radical, no dot on Y, to give a product which is a free radical and something else which isn't a free radical. Okay, that's propagation. Of course, if you get 2 free radicals joining together, that's termination. If you, and the other thing you get, this one here is of course initiation, the opposite of termination, when it breaks up to form 2 free radicals. So this one is termination, that's no good, 2 radicals coming together. This is also termination, that's initiation. This is the only one that's propagation, D. Okay, which compound can react with ammonia to produce propylamine? Let's just draw the structure of propylamine. Is like that. And if you remember, that is formed by nucleophilic substitution from a haloalkane. I'll put bromine on there, but it could be chlorine or iodine. And you're going to react that with NH3. And that's going to go there like that, and that's going to come off. Right. That doesn't react with ammonia. It's an alkene. Ammonia is a nucleophile. So it's not going to react with alkenes because they react with electrophiles usually. The alcohol, it won't react with the alcohol. Okay. It will react with this one. And of course, it won't react with an alkane. So C is the answer there. Okay, which statement is not correct about that molecule? So let's draw it out, okay? I don't like looking at those, and it's confusing. People, don't do it in your head, draw it out. It takes 2 seconds. So draw that out. You're going to get, there's your double bond. You've got 2 hydrogens on that carbon. On the other carbon, you've got a CH3 and a CH2Br. Okay, the way I've drawn it there. It displays EZ isomerism. Well, it can't around that double bond because, look, this carbon is attached to 2 hydrogens, so it doesn't matter if you swap them about. That's wrong. It can form an addition polymer. Yeah, it can, because it's got a double bond. Anything with a double bond, then it can polymerize with itself. So the double bond breaks and it forms a polymer. You know, if I just draw it like that, and it's going to form repeating units like this. So X, Y, W, and Z. Okay, that's a polymer, so it can do that. It will react with electrophiles. Yes, it will, because it's got a carbon-carbon double bond. It will decolorize bromine. Yes, it will, because it's got a carbon-double bond. So A is the only one which is not correct. Again, let's draw this out. Which compound can be oxidized to form that? So I'm going to draw it out. We've got this carbon here has got 2 methyl groups attached to it. And a hydrogen. And then it's got this, which is a carbonyl, so it's a ketone. And you've got a CH3 there. What compound can be oxidized to form that? Well, let's just see. To oxidize that, it's come from a secondary alcohol, hasn't it? And what we need is we need to get rid of that, and that becomes an OH. Right, so if you oxidize that, you get the red thing. Okay, so we're looking for that alcohol. What's that called? Let's just see what it's called. It's called 1, 2, 3, 4 is the longest chain. It is called, and it's butanol, isn't it? But we've got to remember we've got a methyl group on number 3, so it's 3-methyl butanol. Is that there? It is. There it is. That's our answer. So always draw it out. Don't try and do these things in your head, because you think you're saving time by not writing it out. You're more likely to get it wrong. It's not saving time. Right. 19. Which species can act as a nucleophile? Now, to be a nucleophile, you need a lone pair of electrons on a preferably an electronegative atom. Okay. You need a lone pair of electrons, and hopefully it can be negatively charged. Doesn't have to be, though. Right, this one can't be. It's got 4 bonding pairs and no lone pairs. This one could, because you've got lone pairs on the oxygen, because oxygen, of course, always forms 2 bond pairs and 2 lone pairs, so that's okay. This one couldn't, because carbon never has any lone pairs. It forms 4 bonds, 4 bonding pairs, no lone pairs. Hydrogen hasn't got any electrons at all, so it definitely hasn't got a lone pair. And so B is the answer there. Not something we'd really think of as being a nucleophile, maybe in year 12, but it could act as one because of the lone pair. 2. Which alcohol forms a mixture of alkenes? A mixture of alkenes when dehydrated. Right, let's have a look at that. Let's do propan-1-ol. Propan-1-ol is like that. Now, when you dehydrate an alcohol, you remove the OH and the hydrogen from the carbon next door. Okay. Right, now that can only form, it's only got 1 carbon next door, so it can only form a double bond there, only form 1 product, so it's not that. Propan-2-ol, and I will see there that that's not going to work either, because, right, yeah, you have got 2 carbons next door, right, but let's draw that on green and that one red. Right, you're going to, if you remove the red one, you're going to end up with a double bond there. That's propene. If you remove the green one, you're going to get double bond there, but that's still propene, isn't it? Because it's symmetrical, so it's not that one. So you can probably see from this example that pentan-1-ol, you can't dehydrate. That will only give you 1. Okay, if I just show you there. So if I rub that off, pentan-1-ol is just the same. It's just got more carbons there, but you will only give you a double bond in that position. But if you get pentan-2-ol, well, that can give you 2 alcohols. Let's just see why. There's my 5. Okay, got an OH there. Let's do that one. That one's a red hydrogen. That one is a green hydrogen. If you remove the red hydrogen, you're going to get the double bond in position between 2 and 3. That's pent 2-ene. If you remove the green, you're going to get the double bond between 1 and 2. That's pent 1-ene. So D is the answer there. Okay, 21. Which compound has the highest boiling point? Right. Now we think about intermolecular forces, and let's think hydrogen bonds are the strongest intermolecular forces. So can any of these form hydrogen bonds? Although they obviously can't. Yeah. Right. Aldehydes. Can they? This is an aldehyde. Okay. Can they form hydrogen bonds? Well, they can't because the hydrogen is not. This hydrogen is not attached to an oxygen. It's attached to the carbon, so it's not sufficiently delta positive enough. Carboxylic acids, can they form H bonds? They can, because they've got a hydrogen which is attached to an oxygen that is sufficiently delta positive there, and of course you've got the lone pairs on the oxygen. So that one there, you can get H bonds, so that's going to have the highest boiling point. Okay, which compound could not be produced by reacting 2-bromo-3-methyl-butane with sodium hydroxide? Okay, right. So what have I drawn there? I have drawn 2-bromo-3-methyl-butane. Okay, so let's see there. Right. So we're going to, all right. Now, of course, sodium hydroxide, we've got to be careful because sodium hydroxide can do a couple of different things, can't it? Let's have NaOH in aqueous solution. It's going to act as a nucleophile, and we're going to AQ, nucleophilic substitution. So we do that, get rid of that bromine, put an OH there. What have we got there? That is 1, 2, 3, 4. That's butanol, 3-methyl-butanol. So yeah, you can produce that one. That can be produced by nucleophilic substitution. Of course, now if we use NaOH in ethanol, you can get elimination. That's very similar to what we were talking about before, dehydration of alcohol. When you eliminate, you remove the bromine and a hydrogen from the carbon next door. Okay, so it's got 2 carbons next door, so you can remove the bromine or you can remove that one there. Now let's look at the blue one. If you do that, you form that compound, which is 3-methyl-but-1-ene. That's that one there. That's what this is. 3-methyl-but-1-ene. So you can produce that. Or if you do it in that one, you're going to end up with the double bond there, which is 3-methyl-but-2-ene. So yes, you can get that one. So that means you can't get this one. 2-methyl-but-1-ene, you can't get that because the methyl group has moved from position number 3 to number 2. There's nothing we know about that can make a methyl just hop positions like that. So A is the wrong one there. That's the one you want to choose. Okay, the infrared spectrum of an organic compound is shown below. Right, what could it be? Which one could it be? Right. Now, let's look at this. Of course, everything 1500 and less is the fingerprint. Forget about that. This one, which I'll draw here in red, the shape of that alone is very characteristic of a carbonyl group, C double bond O. So we've got something with a C double bond O in it. And of course, hopefully you would recognize that this broad peak here is definitely the alcohol, not of an acid, sorry, it's an OH of an alcohol. It's in the right range, and also with the alcohol, remember this is actually the CH peak that gets swallowed up with the acid, but with the alcohol you can see it's 2 separate ones. So it's something that contains an OH and a C double bond O. It can't be ethanoic acid because that's an OH and an alcohol OH. It's not that. 4-hydroxybutanone, right? That would be, you've got and you've got a ketone there, and you've got an OH there. It could be that one. You've got the two groups you want. It can't be propan-1-ol because there's no carbon-carbon double bond in propanol, propan-1-ol, and it can't be prop-2-ene-1-ol because you haven't got the CC double bond. The CC double bond is in a slightly different place. It is a bit further to the right, very close to that, but that one is in the wrong, slightly in the wrong region. Also, you can tell from the shape that it's not CC. CC bond tends to be like more spiky and short at the top like that. But you can tell from the wave numbers alone. So you've got to contain an alcohol and a ketone group, or C double bond O group anyway. Right, that I think is the last question on the paper. Oh no, it's not. We've got one more. Right, okay, number 24. The heat released when 1 gram of ethanol undergoes complete combustion. Okay, what is the heat released by each molecule in joules when ethanol undergoes complete combustion? Okay, so we've got to use the Avogadro constant here. Okay, so, all right, we need to use, when 1 gram of ethanol, okay, so how many moles is in 1 gram? Let's do that. Moles ethanol in 1 gram is equal to mass over mR is 1 divided by 46 is the mR of ethanol. That gives us okay, 1 over 46. Right, so that's number of moles. I won't bother working that out. Now that was so. Right, that releases 29.8 kilojoules. That many moles. Okay, so let's work it out for 1 mole, shall we? Right, so we know that delta H is equal to Q, the heat released, divided by the number of moles. So delta H, that's per mole, is Q. So they tell us it's. I'm gonna convert it into. I'm going to convert it into joules. So that's 29.8 times 1,000 divided by the number of moles, which is 1 over 46. So that is equal to 1,370.8. Actually, let's get rid of that and we'll stick it in kilojoules. Kilojoules per mole. Right, that's how much per mole of ethanol, but it wants us by each molecule. So how many molecules are in 1 mole was the Avogadro constant. So there is the heat per molecule is the amount per mole, kilojoules, divided by 6.022 times 10 to the 23. Okay, and that is equal to right, we've got joules over here, so I'm going to convert that into joules. So that's 1370.8 over that. That is equal to 2.27 times 10 to the minus 18 joules. And that is question A. That is answer A. Okay, so that is the end of the 2019 paper 2.